Log scale is actually really simple. Calculators do logs now. When I was a child, we had to use log tables. That was hell. But it's much better now, much simpler. I hope you have a calculator that will do logs with you, because I really want you to practice this. On the exam, there will be log conversions you have to do. And so, you really just need to practice this. All right. Just like last chapter, everything starts with water. We talked about water. We talked about the differences in electronegativities between hydrogen and oxygen. And we said that there were dipoles associated with these covalent bonds. Because of that, there's a molecular dipole in water, where the bottom half, where the hydrogens are positive, and the top half, where the oxygen is negative. This is an electrostatic potential map. Again, this is the positive region in blue, and up here we have the negative region in red. Now, we talked about the importance of this in terms of dissolving things. We know that water is capable of dissolving ionic compounds. The way it does this is that it will take the individual ions and it will wrap around them. For something like a chloride anion, it will take the negative portion of the water dipole and stick it as close as it can to the anionic charge. For the sodium cation, you get the the negative end, the oxygens, all pointing here at the positive charge. The net effect here is that this water dipole allows you to disperse the positive charge over a large number of molecules. Water is unique in this ability. It's really the best compound we know to allow it to do this. Water also forms hydrogen bonds with itself. The same dipole effect. We have the negative end with the oxygen, the positive ends here with the hydrogens, and they form hydrogen bonds. Water is in a very extended hydrogen bond network. Now, this is a rendering of a cluster of waters. And we looked at this last time. And the thing that I tried to point out to you was just exactly how associated these water molecules and these hydrogens are. This guy, this hydrogen, is half swallowed by both of them. There's a lot of energy associated with this. Now, hydrogen bonds make and break 10 to the 6 times per second. So, they're very short-lived, but you get enough of them together, and it's a real source of interactive energy. Well, there's one other thing that can happen with a hydrogen bond in water, just plain pure water. Let's imagine we have 2 water molecules sitting here, happily hydrogen bonding with each other. All we have to do is put in just a tiny nudge of energy. Tiny bit. Remember how consumed this hydrogen was by both of them. A tiny little nudge of energy, and by George, hydrogen can transfer from one to the other. When you do that, you form H3O. This is hydronium, positively charged. Down here we have hydroxide. It's negatively charged. Now, I said that these things happen very quickly. Again, 10 to the 6 times per second. And so this hydrogen can be transferred back again. And now we have 2 waters again. And this goes on and on and on and on and on. The bottom line here is that if you have absolutely pure water, at 25 degrees centigrade, at any one time, there will be 1 times 10 to the minus 7 molar hydronium and hydroxide in absolutely pure water. Hydronium and hydroxide, and the concentrations of both of these, they're identical, are 1 times 10 to the minus 7 molar. Now, whenever I think about this, I just think that, gee, we're taking neutral species and we're making a pair of ions. These ions are very highly charged, and nature really doesn't like things that are charged. So why does this happen? These are electrostatic potential maps of hydronium and hydroxide. And again, huge blue up here, big positive charge, big negative charge. The reason that this happens at all is that water, being as unique as it is, can stabilize these. This is the hydronium that we just saw, H3O, positive charge, big blue ring around it. We flip it over. See, it's a whole big blue bottom. Very, very positive. Water, however, surrounds this thing. If we take 1 hydronium ion and we place 3 waters around it, only 3, we can calculate the electrostatic potential map for this entire complex. Here's our hydronium, again the big blue bottom here. And we're going to calculate where the electrons are in this whole 4-water complex. And when we do this, we wind up with something that looks like this. The big blue guy that was right here in the middle is gone. And actually, for the middle guy, you can see a little bit of yellow, which means that even these 3 waters have been able to disperse this positive charge over this area. It's amazing, actually. But let's take it to one more level. I'm going to surround this hydronium ion with 7 waters. Now, 8's the magic number. There's 1 missing right on top here. Because we couldn't see it if it was really there. This is our hydronium in the middle. And again, it's got this huge, big blue thing. Yeah, green top. Very, very local positive charge. But if we calculate the distribution for the whole complex, we get something that looks like this. Now, this is our hydronium right here in the middle. Not only is it not blue, but it's red now. The waters around it have sufficiently dispersed the charge so that you can't even tell that this is a positive center. Once again, here it is. Big blue bottom, green top, totally dispersed into all the neighboring waters. Water is just amazing at doing this charge dispersal. So, okay, water hydrogen bonds does it better than any other compound that we know of. It also disperses charge better than any other compound that we know of. What happens if you take a polar compound and put it into water? Let's look at our friend hydrogen fluoride. We've looked at this before last chapter. We know that the differences in electronegativities between the hydrogen and the fluorine are great. And because of that, the covalent bond here is really highly polarized. We have a very positive oxygen, a very, very negative fluorine. Let's look at this as a ball and stick model. We have water hydrogen bonded to an HF. Now remember, this is the negative end of water, the positive end of HF. They're hydrogen bonded. And just like with water itself, all it takes is one little tiny nudge, and by gosh, the proton just zaps over. Now, I say a proton because what is it zapping over as? Oops. Well, okay. It's moving as a hydrogen, but it's leaving the electrons behind. So therefore, it's a proton, isn't it? So our water is now positive, and our fluorine is now negative. In terms of a chemical equation, we can write HF in the presence of water will form hydronium, that's this guy, and fluoride, anion. Now, just like we saw with water, this reaction goes both ways. We can donate the proton here to form the ions, or we can take the hydrogen back and get back to a neutral state. This reaction, again, goes on about 10 to the 7th times per second, handing the proton back and forth and back and forth. In chemistry, this is what we call an equilibrium. When we have an equilibrium, that's a reaction that goes both directions rapidly. We refer to, or we show this using a double arrow. Now, it's not a double-headed arrow. In general chemistry, you would see that that's a totally different thing. But this is a double arrow, and this shows that the reaction goes this way and this way very rapidly and concurrent. It's an equilibrium process. So this is the equilibrium dissociation of HF. Think about what we've done here. This is a covalent bond, and we've broken it. And we've produced hydronium and an anion. This defines an acid. According to the Bronsted definition, anything, Bronsted is an ancient organic chemist actually, but did very good acid-base work. But anything that donates a proton is defined as a Bronsted acid. Anything that accepts a proton, so the back reaction here, fluoride is accepting the proton here to go back, that's a Bronsted base. Bronsted acid donates a proton, Bronsted base accepts a proton. Now, when you have an equilibrium, the equilibrium could lie in the middle. If it was in the middle, it would mean that this rate and this rate were identical. So that means at any one time, if you take a snapshot, you would have the same amount of these guys as you do these guys. The same amount. If the equilibrium, if the rates here are different, so that you wind up with more hydronium than you do acid and water, that's what's called a strong acid. The more hydronium you make, the stronger the acid. In chemistry, we have two types of acids we talk about, strong acids and weak acids, and it simply has to do with the ratio of hydronium and the anion versus the acid and water. If you have lots of hydronium, it's strong. If you have just a little tiny bit, it's called a weak acid. Any questions? Well, this is
A strong electrolyte is a compound that ionizes completely in solution. Hydrogen chloride breaks into hydrogen and chlorine ions.
Now, two things that should ring out to you. The young lady and the speaker there refer to this as an electrolyte. What did we learn about electrolytes? Electrolytes make ions, don't they? That lit up a little machine and you got, bright lights. Strong electrolyte. In terms of an equilibrium, what this means is that when you put HCl in water, virtually all of it winds up as hydronium and chloride. Lots and lots of hydronium, strong acid. Other way around, very little hydronium, lots of the undissociated stuff, is a weak acid. Now, she also said that this dissociates completely. Of course, that's wrong. It's an equilibrium. So that means there's always a little teeny tiny bit of this, maybe 1 part per billion. But most of it is fully dissociated. Now, there are a few strong acids that we need to know. We just saw hydrochloric acid. Hydrogen bonded to the chlorine. Again, it reacts with water to get hydronium and chloride. Another strong acid is nitric acid. This is nitric acid here. If this is nitrate. Remember nitrate? NO3 minus. For nitric acid, all we do is take one hydrogen and we put it on an oxygen. That is nitric acid. Very, very strong, very powerful acid. Causes big bad burns, all of that stuff. Nitric acid plus water, nitrate, and hydronium. Perchloric acid, remember the perchlorate anion. Well, we take and we put a hydrogen on one of the oxygens. Again, it comes off. At equilibrium, we have almost all of this. Perchloric acid is another very strong acid. All of these guys liberate 1 hydronium per mole. 1. Now remember we said that this hydrogen flies over without its electrons. So a hydrogen atom without electrons is just a proton, that's all it is. So these are called monoprotic acids. Sulfuric acid. We take sulfate, SO4, and we put 2 hydrogens on the oxygens. When we do that, H2SO4 can lose one of them to form hydrogen sulfate, and then another one to form sulfate. For every mole of sulfuric acid, you get 2 hydroniums. So it's a diprotic acid. 2 protons per mole. Any questions? Well, when we talk about acids and bases and stuff like that, one of the things we use to identify the parts on both sides of the equation is the concept of conjugate acid and conjugate base. This is nitric acid. It's going to lose a proton to form nitrate and hydronium. In a reaction like this, we would say that nitric acid was the acid, we'll call it a conjugate acid, and the corresponding conjugate base is nitrate. A simple bottom line thing to remember. The conjugate base, this guy, will have one less proton and one more negative charge than the acid does. Nitric acid loses one proton, goes to nitrate. This is neutral. It has one more negative charge. Conjugate acid, conjugate base. Any questions? Let's look at a set of problems here. What I'd like you to do with these is to simply identify the conjugate acid and the conjugate base in each of these reactions. Remember, the acid loses the proton to form the conjugate base. Conjugate base has one less proton and one more negative charge. So in our first one, who donates the proton? Well, clearly it's got to be HCl, doesn't it? So we will say that HCl must be our acid. And when it loses its proton, what does it form? Its conjugate base, one less proton, and one more negative charge. Look at the next one. This is sulfuric acid, H2SO4, everybody's favorite acid. Acid, the thing that donates the proton, is going to be sulfuric acid itself, isn't it? It loses a proton, one more negative charge, so hydrogen sulfate is the conjugate base. Our next one here, remember sulfuric acid is diprotic, so we can lose two hydrogens. Well, this is hydrogen sulfate, we just made it here. It's going to donate another proton, so that makes it an acid.
Even with the negative?
That's right. When it loses it, it gets one more negative charge and one less proton. Conjugate acid, conjugate base.
So is it always in that order? Like acid, base, acid?
Well, you could do it backwards. In fact, we'll do it backwards in just 1 minute.
I jumped the phone.
This is nitric acid again. Now, you know, I said many times just how wonderful water is. But ammonia's close. Not quite as good as water at doing anything, frankly. But it is close. Nitric acid can dissolve in liquid ammonia. And when it does, it forms ammonium ion and nitrate. So, our acid here is simply nitric acid. It'll lose a proton, get a negative charge, and become nitrate. But this is a nice example to look at the reverse direction too. Because if we started with this side of the reaction, what would be the proton donor? Who's donating the proton? Who's the acid? It's going to be ammonium.
Because
It's
it has
going to donate the proton back to nitrate to form ammonia and nitric acid. So in this direction, this is the conjugate acid, and that's the base. Now you could do the same thing with all this. We say hydronium with the acid, chloride would be the base, and go backwards. So these things go both directions, and you could use the definitions in both directions. Just remember, acid donates a proton, and it forms the conjugate base. Now, there happens to be a neat little tutorial for this called conjugate acids and bases. In this, you have blanks that you're supposed to fill in to complete this equation. Well, when you enter this online, look at the order that they're done, fluoride and hydronium, and you want to enter that same order on this side, okay, because that's just the way it was. So, what we're doing is let's look at this and let's fill in the species that are on this side of our reaction. Start with fluoride. What is the conjugate acid? Remember, the conjugate acid had one more proton and one less negative charge. And so very simply, proton or the conjugate acid here must simply be HF. Look at the water or hydronium here. What's the conjugate base for water? Conjugate base will have one less proton, won't it? So H3O minus one proton is simply water. Yeah,
Why does anything get subtracted if it's an addition product?
you have to speak up on the hold.
Why does anything get subtracted from the species or the compound if it's an addition product?
Well, if you look at the finished equation, you have no problem looking at this and saying HF is the acid, donates a proton to the water. This is our conjugate base. In the reverse direction, hydronium is the acid, and this is the conjugate base. So remember, these things go both ways. Let's do another one. This is chlorate plus hydronium. Now, this is actually a reaction in the reverse direction. The acid species here, the thing that's going to donate the proton, has got to be hydronium, doesn't it? The thing that's got to accept the proton here has got to be chlorate. So if you look at chlorate, you say, what is its conjugate acid? Its conjugate acid will have one more hydrogen and one less negative charge. One more hydrogen, ClO3 minus, so one more hydrogen, one less negative charge. This has to be HClO3. What's this block? If we lose this proton here, what we form? Water. That's it.
So you basically
Pretty
just put-
simple, isn't it? Let's do one more. Hydrogen sulfite plus hydronium. hydrogen sulfite plus hydronium. Our proton donor here has to be hydronium. So this is going to be the acid, that's the base. So we look at hydrogen sulfite and we say, what is the conjugate acid? Conjugate acid will have one more proton and one less negative charge. And that makes it H2SO3, sulfurous acid. Over here, if hydronium loses its proton, what does it form? Water. So it's a fairly simple concept. Things that you have to remember when you're doing problems with conjugate acids and bases is that they have to be the same compound. They must only differ by a hydrogen and a charge. We can also do strong bases. We get strong acids. We say that strong bases, when they're put in water, fully ionized, just like HCl. It's an equilibrium, so there's maybe 1 part per billion of this in there, but almost all of it is sodium and hydroxide. Now the thing about a strong acid and a strong base is that they neutralize each other. If we take a hydronium from a strong acid and we take 1 mole of hydroxide from a strong base, they react and they form water. So you start off with a solution that's very basic, another one that's very acid, very acidic, and you wind up with a neutral solution of water. We'll see in a bit, this is called a neutralization reaction. Now, this is my version of how to show this on a slide. This is supposed to represent HCl and water, okay? So we put HCl. It ionizes and forms hydronium and chloride in water, strong acid. In this little circle over here, we have sodium hydroxide and water. 1 sodium, 1 hydroxide. When we take these and mix them together, the hydroxide is going to pull a hydrogen off of here to make water, and the sodium is just going to go along for the ride. We make water, and we have sodium and chloride. We take a strong acid, a strong base, what do we wind up with? This is an important sentence to remember. Strong acid, strong base, we wind up with a salt and water. A salt and water. Any questions? Now this is what we would call a neutral solution. Why is it neutral? Because it has nothing more than a salt and water dissolved in it. But remember, whenever you have pure water, what do you have? Pure water always undergoes the AUTOPROTOLYSIS reaction. It always forms 10 to the minus 7 molar hydronium and hydroxide. So pure water just plain pure water always have 10 to the minus 7 molar hydronium and hydroxide. Whenever we speak of a neutral solution will always have 10 to the minus 7 molar of these guys.
Molar?
Molar, moles per liter. All right. Let's say that we have HCl and sodium hydroxide. They're going to react to give sodium chloride and water just like we saw. We have 125 mils of 0.025 molar sodium hydroxide, so that's this. We're going to react it completely with 125 mils of HCl solution. What's the concentration of our HCl solution? Well, we look at our equation. 1 mole of sodium hydroxide, 1 mole of HCl, right? Now we look at our problem. We have here a concentration, moles per liter, and we have a volume. It's in milliliters, but we can do liters, that's okay. What do we remember? Concentration times volume gives us moles. We know that. We say that at night. Remember? Concentration in molar times volume gives us moles. So we can take our concentration and our volume of sodium hydroxide and know how many moles that is. And once we know how many moles that is, we look at our hydrochloric acid solution, we have a volume, therefore we can calculate a concentration. Remember this, please, concentration times volume is moles. We will use this 100 times today.
That is, from chapter 5?
Yep.
No wonder I'm lost.
Oh, that's right, you
I
are
was
here.
in here. I'm like, what?
Concentration times volume is moles. All right, we have a concentration here, moles per liter. We have a volume. I converted milliliters to liters. Divide by 1,000. So I simply multiply these together. My liter and per liter will cancel. And I get 3.13 times 10 to the minus 3 moles of sodium hydroxide. Now, turning to the HCl. We know we have 3.13 times 10 to the minus 3 moles of sodium hydroxide. And again, we're in 0.125 liters. But because this is 1 mole of each, we also must have 3.13 times 10 to the minus 3 moles of HCl. Because 1 mole of sodium hydroxide reacts with 1 mole of HCl. So, if we know moles and we know liters, by gosh, we know moles per liter, don't we? And that's our concentration. This is a classic titration problem. If you go to general chemistry, you will do titrations just like this, nothing. It's just what you do in general chemistry. You will take and add, we'll see an example of this later, but you'll take and add a strong acid and a strong base together, and you will calculate the concentration of the unknown species. All right, well, we're going to come back to this type of problem in a little bit. Right now, let's look at some old test questions. In this question, where is the acid that's listed followed by its conjugate base? Remember, acid is a proton donor. The conjugate base must be the same compound, just missing a hydrogen and one more negative charge. H plus is an acid, but HCl does not have one less proton and one more negative charge, does it? In H3, one less proton would be in H2. H, PO4, one less proton would be PO4. HCO3 minus one proton plus one more negative charge. That's the answer. The last one here, this is acetic acid, but here we've added a proton, not taken one away. Conjugate acid, an acid loses a proton to form the base. Another one. Which of these statements is correct? Here we have hydrogen carbonate reacting with water to form carbonate and hydronium, right? Hydrogen carbonate is an acid. Water is its conjugate base? No. Water is functioning as a base, but the conjugate base must be the same compound, just missing a proton. Hydrogen carbonate is an acid. CO2 minus is its conjugate base. This loses a proton to form this. Hydronium is an acid, and this stuff is its conjugate base. No, because these aren't the same compound, are they? And neither is this, and neither is this. The only one that works is this guy. Hydrogen carbonate's an acid, loses a proton to form its conjugate base. One more negative charge, one less proton. One more here. Conjugate acid of hydrogen sulfate would be what? Conjugate acid must have one more proton and one more or one less negative charge. It's sulfuric acid.
What was that you said, the conjugate needs to be one more, one less what?
The conjugate acid, the acid form, loses one proton, and the base will have one more negative charge. Why one more negative charge? Because you're losing a proton. Remember, a proton is positive. So if you lose a proton, the thing you form must have a negative charge.
On C, where's the negative charge? On H2SO4, where is
Well, here we're going backwards. So this is the acid. It loses one proton and gains one negative charge. So H2SO4 becomes HSO4.
So you're going reverse.
This is neutral, and this has one negative charge.
So you're going in reverse.
Right. Like I said, these things go back and forth. All right. Let's go back to neutrality. Remember we said that in water we have the autoprotolysis reaction that goes on constantly. And because of that, we have in pure water, always have 10 to the minus 7 molar hydronium and 10 to the minus 7 molar hydroxide. Everyone see that? Now, when you want to deal with the concentration of things like hydronium in solution, that means that you would have to use these little tiny numbers. 1 times 10 to the minus 7. Chemists decided that that was very inconvenient. Okay? Because of that, they developed what's called the pH scale. Now, all in the world you have to do for the pH scale is remember that the pH is simply an exponent. We said hydronium was 10 to the minus 7. According to this equation, the pH is just the negative of the log of hydronium. The log of 10 to the minus 7 is minus 7. And because nobody likes to be negative, we multiply it by a minus 1. So it's just the exponent. And a base 10 log is simply the exponent to which 10 must be raised to get that number. So again, 10 to the minus 7 is going to be a negative, so we have to put a negative in there. 10 to the minus 7 is going to be set. Minus 7, change its sign, it'll be 7. If we add 10 squared, that's 100, right? The log of 10 squared is 2. It's simply the exponent. If we add 1,000, 10 times 10 times 10, log of 1,000 would be 3. It's simply the exponent here. If we had 2.5, and here's where it gets a little bit less intuitive, the log of 316 just happens to be 2.5. That's why you have calculators today. Again, when I was a child, we had to look these up in what were called log tables. And that was terrible. Now you simply push a button. Just for clarification, whenever you see something like this shown in square brackets, that refers to the concentration in moles per liter. So whenever you see a chemical compound in brackets, square brackets, that means concentration in moles per liter. So pH is minus log hydronium. Now remember, we said several times that if you have absolutely pure, neutral, happy water, the hydronium is what? 10 to the minus 7 molar. Now, if we take the log of 10 to the minus 7, we get minus 7, right? Just the exponent. But the equation says we have to multiply it by minus 1. Therefore, the negative log is 7 for pure natural water. Therefore, the pH of pure water is 7. That's where that comes from. Everybody knows that pure water is pH 7, isn't it? That's because in pure water, hydronium is 10 to the minus 7 molar. Now, if we have more than 10 to the minus 7 molar hydronium, we have more than that. That means that the pH is going to be less than 7. And that's called an acidic solution. If we have less than 10 to the minus 7, our pH will be greater than that. And that's a basic solution. Simple thing to remember. If the pH is less than 7, it's acidic. If it's more than 7, it's basic. If it's exactly 7, it's neutral. Just like we had strong acids, we can have strong bases. And just like we can have pH, we can have POH. And all that is the negative log of the hydroxide concentration. Okay. Well, in a neutral solution, what do we have? We have both hydronium and hydroxide are 10 to the minus 7. So that means that the pH in a neutral solution must be 7, and the POH must also be 7. If we take the two actual concentrations, 10 to the minus 7, 10 to the minus 7, multiply them together, we get 10 to the minus 14. This gives us a very powerful tool here. Pay attention to this one. Under all conditions, if we take in aqueous solution hydronium concentration multiplied by hydroxide, it must equal 10 to the minus 14. It must. Doesn't matter what they are, they must equal 10 to the minus 14. And in terms of pH and POH, pH and POH will always equal 14. Knowing these two things will really make it simple to solve what appears to be fairly complicated pH problems. This concentration times that one must always be 10 to the minus 14. And pH plus POH must always be 14. Let's look at an example. Remember, hydronium times hydroxide is always 10 to the minus 14. If we know one of these, we can always calculate the other. So if I tell you that hydroxide was 5.04 times 10 to the minus 8 molar, what would hydronium be? Well, if this times that is always 10 to the minus 14, and we know this, all we have to do is divide 10 to the minus 14 by hydroxide, and we get hydronium.
What?
We know one of them. We know hydroxide. We know it's always got to be 10 to the minus 14. So therefore, 10 to the minus 14 divided by hydroxide gives us hydronium. Isn't that simple? All right, let's look at our pH scale just in general. If we had 1 molar HCl, by definition, that would be pH 0. Remember, anything below 7 is a strong acid. If we had 1 molar sodium hydroxide, the pH would be 14, a very strong base. In between, blood, sweat, and tears are just a little bit above 7. Seawater, borax, ammonia is just almost 12. Bleach is a little over 12. Down here we have bad coffee, a little over 5. Cheap red wine is around 3. Stomach acid, amazingly, is about 1.5. Very, very strong acid. How do we measure it in the lab? A couple ways. The most accurate way to do it is with what's called a pH meter. pH meter is really just a voltmeter. You have this electronic part here that's a millivolt meter. And you have a glass electrode. It literally is a glass electrode. The tip of the electrode is, maybe thinner than a human hair. So it's very, very fragile. And you set the thing up so that when you put it in an aqueous solution, it'll generate a potential across this very thin membrane. And the millivolt meter simply measures that. You calibrate it, and then you can read off directly what a pH value is. You probably won't use these in lab because you're really clumsy, and the electrodes are about $100 each, so you don't use stuff like that. What you do use is pH paper, $1 a roll. pH paper is actually amazing. It is paper that is coated with indicators. The indicators change color based on pH. You simply dip it in. You can get this really high resolution, actually. Here, for this one, neutral is around 7. This is actually, you can't see the color very well, but it's very purple, or it's a very red, depending upon acid or base. These are some common dyes. In lab, we use phenolphthalein, remember? Phenolphthalein went from colorless to pink as we went from an acidic solution to a basic solution. This is the structure. And what happens actually is you will lose one of these hydrogens off the OH groups, and that's what makes the complex color. A much more fundamental indicator, and you see, some of these are really interesting. Much more fundamental one, however, is cabbage juice. If you take red cabbage juice, if it's an acidic solution, it will turn a fire engine red. Here we are at neutrality. It's the purple of the cabbage. And if you get up here in a basic solution, it turns a horrible, unappetizing green. Basically, if you ever saute cabbage, you make sure that the solution is at least neutral, certainly not green. Nobody likes green cabbage. Any questions? All right, well, this is kind of an experiment, kind of like the experiment that we did. And we're just going to talk about this. This is, once again, the mainstay of general chemistry. Remember, we put an indicator, phenolphthalein, in. It was an acidic solution, so it was neutral. And then you added base, it became pink. Okay? Well, here we have what's known as a burette. A burette has a little stopcock on it, and this is a graduated scale. So you can read a volume here, just like on a little graduated cylinder. And what you do is we will put the acid in here, we will put the base in here, and then we'll slowly let it dribble down until we hit a color change. Now we're going to use phenolphthalein, which again goes from colorless to red. When we're ready to do this, very carefully you will open the burette here. You read the volume very carefully, so you know exactly where you start. Open this up, let it dribble in very slowly, and you stop it as soon as your color change happens. Now you know a starting volume and an ending volume. We are now at the point of neutrality. From that, by knowing the volume and the concentration, we know moles. So we know how many moles we had in our beaker here. Let's go back to that. Now a standard general chemistry calculation would be to take an unknown acid. So you know a volume for your unknown acid. Here we know a volume and a concentration for your base. Volume concentration gives moles. You know a volume here, you know moles. You calculate concentration. Now we're not actually going to do that, but this is just good background for how you measure a neutralization experiment. Any questions? Well, once we hit the first shades of pink here, our solution is neutral. Okay? So we have a neutral solution. If we have a solution with a known pH, so we stick this on our pH meter, this is almost neutral, we can calculate the hydronium ion concentration. Now is when you need to fire up your calculators and play along with it. Here we have a solution with a pH of 7.23. I want to know the hydronium ion concentration. Now it's above 7, isn't it? So this solution is slightly basic. Very slightly, but it is slightly basic. If it was below 7, it would be acidic. Step 1, remember, pH is simply the negative log of hydronium ion concentration. Okay, that's our definition. Step 2, let's get rid of that negative sign. We'll do minus pH and simply have log hydronium. All we've done is multiply both sides by minus 1. We can do that way. Step 3, we're going to take the antilog. Now the antilog is simply the power of 10 that you have to get the number that you're interested in. The antilog. On your calculator, you'll see this as 10 to the x. Now I'm going to substitute in 7.23. What I want to find on my calculator is what is the value of 10 to the minus 7.23. Now here's my calculator. Looks like this. I look at it and I find, oh, there's a log button, and above it is a 10 to the x button. You must make sure you have a calculator that does that. A log button and a 10 to the x. Now, we're interested in 10 to the x here, aren't we? So the first thing you do is you will type in minus 7.23. Once you have that in, all you do is hit the, on my calculator, again, they're all different, that's why you have to play with your own. On my calculator, you hit the inverse, and then you hit this one. And by gosh, 5.88 times 10 to the minus 8. This is the hydronium ion concentration. Simply take your pH, change a sign, and do 10 to the minus pH, and you wind up with hydronium.
So what if you don't have that inverse button?
You don't have that on your calculator?
I have like a shift.
Nope. You need one with log and 10px.
Well, it does have that.
Okay?
I
That's
just-
good.
The way that you answered it, and the way that I answered it, press shift,
Type in,
and then lock.
type in minus 7.23 and hit 10 to the x. Should be the same. Why'd you have to hit two buttons to get there? Inverse and then that, second and that. Everybody's calculator is different. That's why you have to learn to play with your calculator.
Can't you do it in a different way too? Is it another way to do it?
Really, this is the simplest way.
What about 10 to the power of negative 7.2?
Fancy. No, you. Error. Oh, you got it.
No, I did it in a different way.
As long as you get it right.
You say log,
And push.
7.2.
Huh? What do you have?
What inverse is it?
I have log 10 to the x, shift. But when you type in 7.23,
Sign.
which is my shift, I think it's just a shift.
Yeah, see how you do it.
Because minus, minus pretty easy, because for I go, 7 and 10 to
I see.
Right yours? Yeah, and then,
Or you can do 10 to the power of 7, negative 7.22 to make it easy. 10.
Good answer.
yeah.
Again, everybody.
Oh, you got it. So, yeah, it's 10, yours has 10, and then up to the power of minus 7. And then the E minus 8 equals a 10 to the negative. See, it says E minus 8.
That's exporter,
So,
right?
yeah, that means, then you're at 10 minus.
All right, one more time.
Right.
I don't know how to use it. I got my finance. I use it, but I never use it. I just do it on everything on paper because I can't see it.
All right,
I know a few things, but you do it.
all right, I'm back to the game.
But I know you could do like for the business.
Yeah, it's supposed to. And this one,
Let me see if
I could like, what's one? Do it
You
now.
need to somehow express
Yeah.
this.
Yeah, I can do that. I have another one that, well, my boyfriend was using it in college, and then he gave it to me. And then I was using that one, and he wanted it back, so then I was just like, I bought him for the copy. Can't take a copy. He bought me this one, but nothing is programmed to it, so.
I tried YouTube and everything.
They have it.
Yeah, I have it.
And I saw a video for this
It took me a damn forever just to clear it. Send it back to the factory settings.
Oh.
Okay. I will type something or do something on
Yeah, this one's giving me weird. When I do like 1 minus like 0.998 or something, instead of saying like 0.002, I'll be like e to the negative something. It's just like, what?
Yeah. So I had to clear it. I forgot how I did it.
Alright, so somebody needs to figure out
I'll
what
go
fixed to
creating
solve.
like a workout police or something.
I'll get it.
Yeah.
Wow. All right.
You know what I did? I did the same thing.
Now, there is one thing that I'm going to tell you about this that that we're really not going to do on an exam or whatever. And this is the significant figures for these calculations. When you have if you look at this, I gave you 7.23, right? This answer is really has 3 digits. You might look at that and say 3 significant figures. But it really doesn't. Because a log, this number 7.23, actually consists of 2 things. The characteristic, which is the first number, and the mantissa, which is the second number. The second, anything after the decimal point here, that's the real number. First number is the exponent, the second one is the real number. And there are only 2 digits here, so this is really only 2 significant figures. So this really is 5.9. So just so you know that, but again, we're not going to do that on exams or whatever. Now, those of you that have figured out how to do that, take your calculators and let's just see if we can do these things. If I tell you the pH value is 4, what's the hydronium? Remember, we want to take 10 to the minus pH. So this is simply 10 to the minus 4, isn't it? So hydronium, 10 to the minus 4, is just that. If I tell you the pH is 12, then 10 to the minus pH, this would be 10 to the minus 12. Now it gets a little more complicated. You would type in minus 5.5 and hit 10 to the x. And that's 3.2 times 10 to the minus 6.
Wait, what do you put? 10? 5.5 times 10?
My 10 to the minus 5.5. Remember, it's 10 to the minus pH. This is going to be 10 to the minus 1.32. And finally, this last one. If I tell you the pH is 7.025567, and you really can't measure it that closely, is this solution acidic or basic?
Slightly basic.
Very slightly basic. You got this, don't you?
I got a question.
All right.
When you put it in the calculator, it don't come out like that. It just come out like first.
If you're doing it right on your calculator, and you type in minus 4, and then hit 10 to the x, you should get 1 times 10 to the minus 4. Remember to change the sign, and then do 10 to the x. All calculators are different. You know, that's why you need one that you love, that you know how to do this, because you will have to do very simple conversions like this on an exam. Make sure you know how to do this. What if I ask you the question backwards? If I say my hydronium is 7 times 10 to the minus 7, what's my pH? Think about your definition here. If our hydronium is 7 times 10 to the minus 7, then the pH is just the negative log of this, isn't it? By definition. Here's my calculator again. Mine is so simple. Here I'm going to type in 7.04 times 10 to the minus 7, the whole number. Then I'm going to find my log button, and I'm going to push it. I'll pause while you push your log button.
You're gonna push the log button or the inverse?
The log button, because you want the log of this. We're going pH, so we
So
want
you're going
the log.
you're not reversing.
Not anti-log, we want log. So type in 7.07 times 10 to the minus 7. Hit the log button. And you get minus 6.15. Now to get the pH, all you have to do is multiply that by minus 1.
Say about minus what?
Minus 1. Just change the sign.
I got
7.04 times 10 to the minus 7. Type that in. Hit the log button.
Jesus Christ.
So I have that, and then if I press the log, it just tells me to enter a log.
7.04
Okay, let's clear it.
times minus
Now,
7.
Oh,
again,
okay.
everybody's is different.
And then do I still do times 10 to the negative 7? Oh yeah.
How about that?
Nice.
Yes!
You know what?
So you got it?
You know, life is full of minor trials. Nathan, you don't have a calculator?
No, I do not.
Not all nine.
I have one you could,
That's all right.
you could try to play with.
I trade you calculator. Mine too.
It's all right.
Where's my log button? Here's the log button, and the 10 to the X.
How did I get you? 6.5.
I'm gonna try it.
You just literally go back log, and then you put the equation inside the log. And you put enter. That's why you need like the log button. Or just press log first.
How long here?
You can have the log.
Find the log.
Depending upon your calculator. With this one, again, you type in the number, simply hit the log button, and then change the sign.
Wait,
No, must be nice.
Why don't you just
So-
put
Pushing it, girl. Pushing it. There you go.
You get it? I don't know.
What is this, TIA 90?
89, titanium, Texas Instrument. Organic.
Oh.
All right, is everybody good here?
I guess.
Oh,
Well, I will wait for you then,
Figure it
okay?
out.
TIA 89 does not have a longer base, but press catalog, go to answers, the catalog, navigate to catalog. So, catalog,
All over here.
yeah, and now you just have to go there.
All right, while everybody's having fun with this, take these hydronium values and convert them into pH values. Now type in 1 times 10 to the minus 4, and then simply take its log, change its sign.
Did you figure it out?
Yeah, the first one.
Well,
So they just leave it?
is it long or long range? It's long range.
Yeah, long.
Yeah, just log. So with your calculators, you hit log first, type in the number, then change the sign.
So I got long, each 1 times 10 to the negative 4.
And I got missing
So it's -4.
Equals,
I got negative.
negative 4.
right, you always do, then you change the
So
sign.
it'll be a 4.
It'll be a 4.
So you change the negative to a positive?
All right, try it with 5 times 10 to the minus 4.
So it would be 3.3.
3.301.
So how many times? When do we round the?
Don't worry about that.
Okay.
For the next one. 1.37 times 10 to the minus 8. Is that acidic or basic? That's less than 10 to the minus 7, so it's basic.
Negative
7.86.
I got this now.
All right. 7 times 10 to the minus 7.
So 8.
6.15. Do the last one here for me.
So,
4.336.
5.66.
4.34. All right.
That's what I got.
Long,
second,
6, 1, times 10. Okay. I wasn't doing that.
All right. Now, of course, there's a tutorial for this. This starts off very simple. If our hydroxide is 6 times 10 to the minus 11, what's our pH? Now think about the logic here. If we want to know the pH, we need to know hydronium, don't we? Right? But remember our fundamental relationship. Our fundamental relationship here. Hydronium times hydroxide is always 10 to the minus 14. Always. So if we know hydroxide, we can easily calculate hydronium. Once we know hydronium, we just take its log. Change the sign, and we have pH. We're gonna take 10 to the minus 14 divided by hydroxide to get hydronium. So we were given hydroxide was 6.11 times 10 to the minus 11. 1 times 10 to the minus 14 divided by that gives us this guy. Remember I kept telling you the tutorial on exponents was going to be important? Remember? I did that, didn't I? Now we have hydronium of 1.64 times 10 to the minus 4. So all we have to do is take its log, change its sign. Anyone have an answer yet? The log of 1.64 times 10 to the minus 4.
Like
3.79.
7, 8. Oh,
How do you enter the 10 to the minus 4?
Again, that depends. Your calculator, I believe, has
Well, I
an
added
exponent.
the TI-83.
Okay, has an exponent. It should have an E or something like that.
Yeah.
That's like that exponents.
I know I just did that. And then you put the number, right?
If our hydronium is 2.8 times 10 to the minus 3, what's the pOH? Again, all we have to do is calculate hydroxide, right?
So you divide?
Divide 1 on 10 to the minus 14 by this, and that gives you hydroxide.
So divide.
Divide 10 to the minus 14 by our hydronium, and that gives us hydroxide. So you simply take the log of that, 3.5 times 10 to the minus 12, and change the sign.
$11.45.
11.46. But that's, again, the tutorials have 5% slot built in, so it doesn't matter.
4.5.
All right, this is my favorite one. Here you're given a table, and you're given one value, and you have to come up with all the rest. So we're given a pH here. How do we get hydronium? 10 to the minus pH. However your calculator does that, 10 to the minus pH.
Now 1.48 times 10 to the negative 11.
Oh, I see, okay. Hang on to that answer. I forgot. The first thing I did was the easy one. I did pOH. Why is that so easy? Because pH and pOH are always 14, aren't they? So all you have to do is take 14, subtract our pH value, and you get 3.17. Now we're going to do the one that I thought we were doing first. So 10 to the minus 10.83.
So that one,
That's our hydronium over here.
then I got 1.4, I guess rounded up to 8, leaves 10 to negative 11.
I don't think so. I think it's going to be much less than that.
Yeah, he's gonna.
Try it again. It should be 10 to the minus 11.
Yeah, that's what I got.
Oh, okay. All right, you got it.
Yeah.
Now, how do we get hydroxide? Since we calculated POH,
1.48.
we just do 10 to the minus 3.17. 10 to the minus 3.17. And it's about 6.7 times 10 to the minus 4.
I'm lost.
Yeah.
I'm just lost.
Step one, first thing I did was the easy one. I know that pH plus POH is always 14, right? Always 14. So I simply subtract and I found POH.
14
Would you get that 1.48?
14 minus, what'd you get that 1083 from?
The problem.
Oh, it gave you that.
Yeah, we were given that.
So POH.
Well, that's step
So
one.
your pH is.
Now we know pH and POH. So to get hydronium, we do 10 to the minus 10.83. To get hydroxide, we do 10 to the minus 3.17.
H.
What does pH mean?
Minus
What's like the word, what does pH mean?
P is an abbreviation for negative log.
Okay.
So this is
And then the-
negative log of H.
Oh, okay, that's why you use the 10
Right.
point.
Negative log of OH.
Negative log of-
So
okay.
how did you determine that 10 minus
10 to the minus 10.83. Feed it to your calculator.
10 to the minus 10.83 equals 1.479
You got it. You see?
minus 11. So you round it off
Don't worry
to
about
the
it.
digits. And then
Let's
you
try one
say,
more. Here I give you hydronium. Let's fill in the rest.
1, 2, 3.
So the pH would be.
First thing let's calculate is hydroxide.
OH,
Okay, how do we do hydroxide? Remember,
you divide.
right, hydronium and hydroxide is always 10 to the minus 14. We're going to take 10 to the minus 14 and divide it by this stuff.
Yeah.
So would it be like 1.23 times 10 to the negative?
10 minus
Oh, just
14
by
divided
10.
by 1.23 times 10 to the minus 3, right?
So you have to do like 1
8.18.
times 10 to the negative 42.
It's the same.
8.13?
Oh,
Yeah.
same thing.
8.13, is that the answer?
8.13, we have a winner.
How are you gonna figure it?
So where's that negative 10, 12 coming
Yeah.
from? I
Um,
got a negative 18.
Me too.
Yeah, so you have 14 and a -3.
Wait a minute.
Now, remember, you should have worked on the exponent tutorial more.
I told you. Told you.
Oh no, because I'm going based on what the calculator is telling me.
All right, now we know hydronium and we know hydroxide. All we have to do is calculate pH and pOH. The log of hydronium. So type in hydronium.
2.91.
2.91.
So you took what?
You take
Simply take the log of 1.23 times 10 to the -3.
So you take 1, 2, 3. Oh, that's what I did at the beginning.
Yeah. And then hit the log button. For hydroxide, we calculated it was 8 times 10 to the -12, minus log of 8.13 times 10 to the -12,
11.08.
So you take
11.09.
Right.
Now, you know, these tutorials, you need to work on. Obviously, most people do, you know, most people do a great job on them. Get lots of points, and that's good. On Blackboard, before our next exam, we will have a quiz, right? We always do. And problems identical to these will be on Blackboard. However, Blackboard has many issues. And so I had to change the format of the problem slightly. On Blackboard, the problem you get will have everything filled in. And the question on Blackboard is, which one of these is wrong?
So
Okay?
can you go one step back so I can see what you have in the bar up there?
Do I go back to the other one?
Well, the one
Well,
that
I
has.
should be able to. It's not letting me for some reason.
Oh, darn Blackboard.
I think you just crashed my
I
PowerPoint.
just crashed. Let's go home.
You just crashed my PowerPoint. Shame on you.
Just in time. 8 o'clock.
Yep, you did.
I did?
Yep. All right.
I want the rock climbing.
Yeah.
No, that without fingers.
But
I
you
don't want my toes spread out.
This one, right? These are the ones I used to.
Yeah, I had those. I used to go hiking.
Yeah.
But I don't like my being like this.
Ripper sells the same ones. Well, without the tools.
Yeah, those are the ones. I want them where they're looking good. They have that rubber sole and it's flat. So it would be nice to do it.
So you hear it?
I know, trying to.
You hear anything? I recommend heavy.
I usually use my chucks because they're clean, or I don't usually shoot them on. Oh, you're talking about the Reebok, like,
The Reebok ones, yes.
I don't like those.
Those are the good ones.
No, because,
Because they're flat,
yeah, but
flat and they're hard.
but the heel is raised, so then it makes it easier for you to be able to lift cover. But then now what I'm trying to do is actually drop the corner and
That
the
is
other.
fine.
Well, my phone is at
This is
1%.
what you get hurt.
Time to go.
This when you do it by yourself.
All right, so let's go back to this guy. This is how it looks like on Blackboard. Now, there's a simple way to approach this. we know that pH plus POH must always be 14, right? If it's not 14, then one of these guys is wrong. We also know that this times that must be 10 to the minus 14. If it's not, one of those is wrong. So, step 1, is this 14? Step 2, if it is, then one of these guys has to be wrong. This is in fact exactly 14, so one of these is wrong. Therefore, simply take the pH, do 10 to the minus pH, and see what you get for hydronium. Take 10 to the minus POH, see what you get for hydroxide.
What?
10 to the minus pH gives you hydronium. 10 to the minus OH, POH, gives you hydroxide. This one is right, this one is wrong, this is the bad guy. Isn't that simple? So this really should be 3.2 times 10 to the minus 4.
And do we have to correct it, or we just have to?
I don't remember.
Okay.
But you have to do something.
So,
Have to figure out which one is wrong. Finally, let's wind up on one of my
switched too
favorite
quick.
problems.
I'm not even halfway done writing and he switches.
But you know, I can push the button so quickly. I will try to go back.
And then it
The
freezes.
last time I crashed the computer, it was all your fault.
Yeah.
I know. Wow. No, it's because you're rushing through the slide and I can't type that fast.
We could have been out already.
Blame it on me. Okay, you may proceed.
All right. Fun problem. We have cheap red wine. We measure its pH, and it's 2.85. I assure you, you don't want to drink this. Not even my father-in-law would drink that. Okay. What I want you to do is calculate hydronium hydroxide and a POH. So same problem, really, except this is about cheap red wine, so it's fun.
So the pH is.
So we know a pH, right? Let's do hydronium. Hydronium is going to be 10 to the minus pH.
What's the pH? 2.85.
So this is 10 to the minus 2.85, right? Hit the magic buttons on your calculator. This should be about 1.4. I think this should be minus 3.
Is it?
Yeah.
0.0?
I got 0.0014.
Me too.
Yeah, 1.4 times 10 to the minus 3.
Yeah.
Yeah, so that's a minus 3, not a 3. Sorry, typo.
Oh, so wait.
To the minus 4?
Nope, 1.4 times 10 to the minus 3.
Minus 3?
So what's the easiest one to do here? If we know a pH, how do we get POH?
1.14.
Subtract it from 14, don't we?
Where did
pH
you get
and
the 1.4?
POH is always, it's there.
Where did you get it from? It's provided,
Yep, 10 to the minus 2.85.
is 1.4?
1.4 times 10 to the minus 3. 0.0014.
Oh, get it. Yeah, got
get pH and POH is always 14. And we know pH, what is POH? Just subtract them, right? 11.15. And finally, we need to calculate hydroxide. If we know POH, we can do hydroxide the same way we did hydronium, can't we?
7.08 and the negative 12.
So you say.
It's going to be 10 to the minus POH. So that's 10 to the minus 11.15. What did you get?
I got 7.08 times 10 to the negative 12.
Got it.
Oh, you run that to 7.1.
Oh, to the minus 10.
All right. Now the really good news is that
7.
this is our last quantitative chapter. Our next chapter, we start the fun stuff. We're doing organic chemistry next. So, then we'll do food and nutrition, and we'll do earth science and radioactivity, and just really fun stuff. So, we have to survive these couple of chapters with lots of numbers. We'll do organic, have our next exam,